Hello, everybody. I hope you all are keeping safe. This video is about Module 14. We are going to cover all the way to example 14.4. As you can see, this module goes from page 457 to page 477. And we are supposed to be covering half the chapter today. In Module 13, we learn all about electrical fields and electrostatic forces. In this chapter, we will learn how electric charges moves in response to the electrostatic forces. So those charges now are going to be moving. And if you remember from previous chapters, movement translates into kinetic energy, and kinetic energy can do work. And of course, everybody's familiar with electricity, and that's just electrons moving. So we are making those electrons work for us. So that's why learning all about this is very, very important. Before we can learn about electrical potential, because this is what we're going to cover, electrical potential, potential energy and potential differences, potential difference and charge in potential energy, conservation of energy in electric potential, capacitors, an application of capacitors, and how television makes its picture. So this is chapter 14. This is about this. Today we're just going to talk about electrical potential and potential energy, and I think maybe we're going to touch a little bit on this. I'm not remembering this very much, but as we go, we'll see what we cover. I'm going to stop at example 14.4. That's where I need to stop. But before we can learn about electrical potential, we need to learn a few facts. First fact number 1. The longer a negative charge particle is allowed to move towards a positive particle, the faster it will travel towards it. There's going to be an acceleration increase. So that's rule number 1 or point number 1. Okay? Let's keep going. Fact number 2. If a negative particle starts at rest, remember these were electrostatic force particles to start with, they were at rest, and suddenly begin moving, we can conclude it has gained kinetic energy. If you remember, kinetic energy is 1/2 the mass of the particle, velocity square. So if it starts moving, now it has kinetic energy. This kinetic energy did not just appear out of nowhere. The first law of thermodynamics tells us that that energy was there all along. This energy comes from potential energy. Okay, so there's going to be potential energy changing into kinetic energy, and we're going to learn how this works in this module. This potential energy comes from the electrical potential, which is abbreviated with a V. A capital V is electric potential, not velocity, but electric potential. And we're going to be learning all about that. This represents an electrical field right here. We have static particles that are creating this electrical field. Remember, coming out of the positive, going into the negative. And if you put a particle that's charged in the middle, it will move. This one is positive, so it's moving towards the negative. And remember, the farther you put this particle, the more distance it is from where it wants to go, the more time it has to accelerate, and the faster it will go. So if it's moving, it has kinetic energy, okay? Kinetic energy. But that just did not appear out of nowhere. It came from the fact that there was potential energy, and this potential energy was created by the electric potential that was created in this electric field by those two charges that cannot move, wanting to be close to one another. Okay? There you go. Let's go to fact number 3. Electric potential, here's your capital V, depends only on the charge that creates the electric field. So here, at least for this this course, okay? Who's creating the electrical field here? We have this plate full of negative charges and this plate full of positive charges. When we drop electrical fields, remember, we do lines that don't cross one another, and that's the arrows that you see here that represents the electrical field. So those two are responsible for the electrical field that's created here, and they are responsible for the electrical potential that will give us the potential energy for any particle that you put in there to move. Okay. In this book, the electric potential will depend only on the fixed charges. For this book, the fixed charges will create the electrical field that will provide the electrical potential to give us potential energy later. Another definition, an electrical field is the region of space around a charge where a positive test charge experiences a force. So there you go. This area right here is your electrical field. Let's move on. On page 457, you're going to find all this information about electric potential. The information I gave you before was done even more explanation than the book gives you. I thought you need more explanation to understand these. Electric potential, the definition in your book says, is the amount of potential energy stored in each point of an electric field. So if you go back to the previous picture, here in the electric field, at each position in the electric field, that particle has a different potential. And there's going to be a lot of words that sound very similar. Potential energy, depending on the position in the electrical field. Okay, so that's what it means. Where you are matters. Okay, the distance from where you're going matters. It is the energy. Electric potential is the energy a charge has due to its location in the electrical field. So position matters. When a body is charged, work is done in charging it. This work done is stored in the body in the form of potential energy. The charged body has the capacity to do work by moving other charges. And then the potential energy will decrease because the kinetic energy will increase. Okay, remember, it transforms from one to the other. It doesn't disappear or it doesn't appear out of nowhere. The ability or capacity of a charged body to do work is called potential. That's where the word potential comes from. Do not confuse electric potential with potential energy. And it's hard because the words sound very similar. You have the word potential there both places. And I'm going to try to be very careful using the right word. Here we go. Next. How do we calculate electric potential? On page 457 in your book, you have a new formula, a new equation that allows you to calculate that electric potential. Capital V for electric potential is Coulomb's constant. You have seen this before. It's the same number we used before, 9.0 times 10 to the 9 newtons meter square divided by Coulomb square, times the charge of the fixed particle, the particle that is not moving. That capital Q represents the fixed charge. And R is the distance. So that's what we mentioned before, that the position in the electrical field was important. And here it is in your formula. R represents a distance that particle is from the moving particle. Okay? I read this already. Let's see here in blue. Electric potential depends only on the charge that creates the electrical field. As you can see, the electrical field is created by the stationary charges, at least in this book, and that's what we have in the formula. In this course, the electrical potential will depend only on the fixed charge. When using this formula, put the charge signs directly into the equation. So remember how in the previous module, we used the absolute value of the charge. So if you had a negative charge, you just use the number, the magnitude without the negative in front. But for this formula, for this module, the charge sign, if it's a positive or a negative charge, counts. So you need to put it in. We use the magnitude, not the absolute value. The units for electric potential are the volt. The volt is just Newton multiplying the meters divided all by the coulombs. That's what it is. So that's what a volt is. Let's look at example 14.1 that is found on page 458 plus in your book. It takes more than one page to do. It reads like this. Consider a positive 3.2 millicoulomb positive charge that cannot move. So this is our fixed charge. What is the electric potential 45 centimeters from the charge. This is just an application of the formula. Let's write the formula. Let me get my whiteboard here. I'm going to my whiteboard, and here we go. Let's see. I'm just learning how to do this, so be patient with me, okay? So we have that our electric potential, V, equals our constant, Coulomb's constant, times our charge divided by the distance. We just need to make sure that our units are correct. So we have everything except that the units are incorrect, so we're going to have to change the units. So let's see. Our potential is going to be 9.0 times 10 to the 9. I'm going to put parentheses here. Multiplying our charge, and if you notice the charge was in millicoulombs, and we don't need millicoulombs because the units here are in coulombs. So you know how to change that. You can divide by 1,000 or just put times 10 to the minus 3 in your calculator. So 3.2 times 10 to the minus 3, and now I have it in coulombs. Everything divided by the distance. What was the distance? The distance was 45 centimeters, but that's incorrect too. The units are not right. You need to have units in meters. So you can divide 45 by 100 to change that into 0.45 meters. Put all of these, put it all in your calculator. Your volume, I'm going to put it in yellow, should be V, the electric potential is 6.4 times 10 to the 7 volts. Okay, volts, you can write it all, volts, or just put the V. But this is your answer. If you don't get this answer after you put all the numbers in your calculator, you're doing something wrong with your calculator. Practice with your parentheses. And this is example 1. Let me go back to my instruction and let's go on. How to convert electric potential to potential energy. How you do that, okay? Because remember that potential and the electrical potential gives us potential energy that then can convert into kinetic energy, which will translate into work later. So potential energy is Q, and Q represents the charge that can move, is the movable charge. And V is your electric potential. Remember we said electric potential provided potential energy. So here in your equation, they are connected now. Okay, and the units for potential energy are in joules because energy is joules. You already know that from previous modules, and a joule is just the Newton's thumb meters. And this was explained to you on page 459. Let's go on. Potential difference. What's a potential difference? Well, it's a difference in the electric potential from one point to another. Remember, the position where this particle is placed plays a role when you calculate electrical potential. So depending on where you are, you have different electrical potentials as a particle, as a charged particle, not you, but the charged particle. Let's see. As the electric potential changes, so does the potential energy. That should make sense because as we saw in this formula, okay, the potential energy is related to how much electric potential you have. I know it's a mouthful, just bear with me. So let's see. So this allows us to calculate the speed of the particle as it moves. Because if we know the potential energy, we can calculate kinetic energy. And in kinetic energy, you have velocity. So knowing potential energy allows us to know how much kinetic energy we have, and that will allow us to calculate how fast that particle is moving. So far, so good? Okay, here we go. Things to know. This is kind of a review, maybe not even more information, but here you go. As the freely moving charge, that's lowercase q, approaches the stationary charge, the magnitude of the electric potential, and thus the potential energy, increases because it had more time to accelerate. Remember? If the equation for potential energy gives us a positive value, what does it mean to have a positive value for potential energy? It means it's increasing. If this one is increasing, kinetic energy has to be decreasing. That's what the law of conservation of energy is telling us. Basically, the particle is slowing down. If the equation for potential energy gives us a negative value, means it's decreasing. Potential energy decreasing translates into kinetic energy increasing. That's what the law of conservation of energy tells us. That means that it is speeding up, okay? That particle is moving faster. And this is the same formula you had before. Here you go. How do we put it all together? Example 14.2 on page 461 reads like this. A negative 5.6 millicoulomb charge, wrong unit, that is free to move, so this is our little q, is placed 68 centimeters from a fixed positive 4.8 millicoulombs charge. If the free moving charge moves 15 centimeters towards the stationary charge, what is the charge in potential energy? What is the charge's potential energy? Did the potential energy increase or decrease? Okay, let me see. Let me go to my whiteboard here and try to solve this for you. Let me get a new page. Okay. Example number 2. I don't have all the numbers, so I have to get my paper, but here you go. Let's draw this for a second. We have a stationary, okay, let me erase and get white. I like to write in white. Okay, we have a stationary charge Q. We have a moving charge, little q. They are a distance apart, okay? And what did they give us? They give us the charge for the stationary charge. And it says that the stationary charge is positive 4.8 millicoulombs. A negative 5.6 millicoulombs charge that is free to move is our moving charge. So minus 5.6 is here. Millicoulombs. There you go. And their place, the initial distance between the two of them, our distance here, equals 68 centimeters. 68 centimeters. Okay. I guess I'm going to have to push it a little bit harder. Okay. Then, of course, they are attracted to one another because one is positive and one is negative. And it says that it's freely moving towards it. So now it's moving this way. And our distance for the movement is 15 centimeters. Okay. Okay. This is the information we have, correct? Well, what is the question here? They want to know the potential energy. How do we find the potential energy? This formula, change in potential energy, says that our potential energy is the moving particle charge. So this right here, times the change in our electrical potential. What is the change in electrical potential? Let's think about this, okay? The change, delta V, equals our final electrical potential minus our initial electrical potential. So we need to find both. We need to find the final electrical potential and our initial electrical potential. So we can find this. We're missing this right here. This is what we're missing, okay? Very good. So let's go to the next, maybe I have enough room here to do at least some of it. How do we calculate the final electrical potential? Well, let's use the formula. That is our Coulomb's constant, the charge. Let me erase this Q. Didn't turn out very nice. Our fixed charge divided by the distance. The final distance is right here. I'm going to put an F so you know that that's not true. Our final distance is going to have to be let's see, is it the final distance? It says moves 15 towards the stationary charge. Let me look at this for a second. So it is not our final. We're going to have to see the difference between those two right here. Okay. That's going to be our final. So we have everything we need. We need 9.0 times 10 to the 9. I'm not putting units because it will take too much space and I don't have it. I know that my units here are incorrect, so I need to change that to coulombs by multiplying by 10 to the minus 3. And I need to calculate what my final position is for these right here. It started 68, but it moved 15 centimeters forward. So basically, our final position is going to be the 68 minus the 15. And if I did my calculations correct, that would be 53 centimeters. We don't need centimeters, okay? We need meters. So you need to divide this by 100 to find your meters. And if you do that, this number is 0.53 meters. Okay. Put all of these in your calculator. Let me get a new page here. If you do the calculations correctly, your final electric potential is, let me find it right here, my numbers, 8.2 times 10 to the 7 volts. Okay? Are we done? No. We need now to find our initial potential, electrical potential. So our initial is going to be our coulombs, our fixed charge, and the initial distance from that fixed charge. We have everything. That's 9.0 times 10 to the 9, parenthesis, this is a 9. Okay, multiplying our charge, and remember that charge was incorrect, had incorrect units, so you needed to change that, multiplying by 10 to the minus 3. And all divided by our distance initially. What was our distance initially? It was 68 centimeters, but centimeters are also incorrect units. You need to divide it by 100 to convert it into meters. So this is the number you need here. Do the math, put all of these in your calculator, and your electric potential initial now should be 6.4 times 10 to the 7 volts. Okay? Now you have both initial and final. So if you do this, final minus initial, you're going to find the change in electric potential. So this is your next step. Find the difference. This one minus this one. Let me get a new page and I'll put the number that I got. And you should be getting the same number because we're doing it together. And also you have it in your book. So you can look in the book to see if you're getting it right. But the change in electrical potential equals 1.8 times 10 to the 7 volts. Are we now done? No, we're not done because that was not what they were asking for. They were asking for potential energy. So remember that is our moving charge times the change in electric potential. And we have everything now that we need, except that our charge, it has the incorrect units. So we need to change that. Minus 5 times 6 multiplied by 10 to the minus 3 to have the right units in coulombs, multiplying this number 1.8 times 10 to the 7. Do the math, put it all in your calculator, and you should be getting a value of minus 1.0 times 10 I should have put this in yellow, but I didn't because I'm learning how to do this. 5 joules. I'm gonna actually put it in a box so you know that this right here is our answer. This is what they were asking for. What does it mean to have a negative number? It means that is decreasing. Basically, the kinetic energy for this particle is increasing. That's why the potential energy is decreasing. Okay, so remember that if you are able to follow the instructions in the book, if it makes sense in the book, you don't have to watch the video. You can skip parts of the video, just move the cursor forward. Now, if we go back to instruction, it says here to do extra practice number 1 and 2 and 3. Once again, I'm going to give you the answer for them. If you have the same answer, you can skip the video that I'm gonna, the section of the video is not a separate video now. The section of the video where I explain the extra practice problem. So let me go to number 1 first. I'm gonna do another page. So we're doing number 1 here, okay? Let me change to white. The answer for number 1, let me get it right here. Your answer should be, maybe I should have put it, I'll go back to yellow. The answer for number 1 is minus 9.8 times 10 to the 10 joules. So if you got this answer, move on to number 2, okay? If not, watch the video to see how this was solved. You can always, actually this one had 2 questions. This is for the potential energy, and for the electrical potential, the answer would be 1.4 times 10 to the 10 volts. So those are the 2 answers that you needed to come up with. Okay. If you got them, move on to number 2, then look at the answer. If you got it, move to number 3, and so on, okay? If you didn't get it, you can try again, or you can watch the video to see how it was solved. So let's go and see how this was solved. Let me get my extra practice problems right here. I'm gonna change pages, and I'm gonna go to white. Okay. So number 1 reads, determine the electric potential 2.5 meters from a stationary 4.0 coulombs charge. What is the potential energy of a negative 7.0 coulombs charge placed at that point? The nice thing about this problem is that they give you the right units. So that's pretty nice, okay? So we're doing number 1 here. The formula for electric potential, okay, trying to start here, equals our coulombs constant, our stationary charge divided by our distance. We have everything we need. So this is 9.0 times 10 to the 9 multiply our stationary charge. There was only one charge here. That was stationary. It's a stationary charge, 4.0 coulombs. So the units are correct. We'll leave it alone. Divided by the distance. The distance was, it was placed at 2.5 meters. Okay? Put all of these in your calculator, and then you should find that electric potential to be 1.4 times 10 to the 10 volts. So if you didn't get this, it's because you did something wrong with your calculator. Okay. Now let's see how we can find the potential energy. Potential energy equals our moving particle, the one that's moving, times our electric potential. We just calculated that. So if you had it wrong before, that's why you probably got the potential energy wrong. The moving particle, the one that's moving, has a value of negative 7.0 coulombs. It's already in coulombs. We don't need to do anything else. And then we place here the number we found before, 1.4 times 10 to the 10 volts. Put all of these in your calculator, and the number you should be getting is negative 9.8 times 10 to the 10 joules, okay? So if you got this wrong, it's probably because you got the electric potential wrong before. There you go. That's example number 1. Another page. Let me put the answer for number 2. So this is the answer for number 2. Remember that if you got this right, you don't need to watch the video for how it's solved. So let me get my answers. I'm going to write them here. They were asking for the potential energy. The potential energy, according to our book, is 0.77 joules. If you got this, move on. If you didn't get this, let's see how this was solved. Let me read first. I like to read them first. It says, what is the change in potential energy experienced by a 0.0018 millicoulomb charge that is originally placed 13 centimeters away from a fixed charge of 0.0078 millicoulombs charge, and is allowed to move to 85 centimeters away. So notice please that the units are incorrect, and that's going to be a problem. Let's draw to see what they're saying to us. We have a fixed charge Q. We have a movable charge, little q. They are at a certain distance. Let's put the values of these charges. The fixed charge is 0.0078, 4 millicoulombs, and the charge that is moving, our little q, is 0.0018 millicoulombs. What else do we know? Its place originally, so our initial distance is 13 centimeters. Let me erase this. 13 turned out kind of weird. So let me back to the pencil. 13 centimeters. Okay, great. And then what? Because they are both positive, if you notice that they are both positive, this one is going to try to move away. So our distance now, our final distance is going to be 85 centimeters. Remember that particles that have the same value, positives or negatives, repel one another. So this one, the one that's movable, the one that can escape, will try to move away. And they're asking for potential energy here. So what is potential energy? Let's write the equation. Is the value of our movable particle, except that this is incorrect. We're going to change these to coulombs, multiplying the change in electric potential due to the fact that you have changed your position. So we do have little q, but we don't have these. This is what we need to find next. Everybody sees that? We're missing that. Okay, let's go up here and get a new page. And let me change to a pencil. And let's see what that is. Change in potential energy. Sorry, electrical potential. I told you that the words are very similar. It's hard sometimes to keep up with what you're talking about. So is electrical potential is our potential final minus our potential initial. So we need to find each one of them. And let's see, how did I do that? I did do it separately. Sometimes I like to do it together, but I did divide it separately. So let's start with our initial today. That is the Coulomb's constant multiplying the charge that's stationary divided by the initial position of that particle that if you saw before, let me go back, is the initial position, okay? This is it, 13 centimeters after you have changed this into meters. So let's go to the next screen. So we know what this is. It's 9.0. If you don't remember, I think the problems give it to you, but we have been using it so many times that hopefully everybody has memorized the value of Coulomb's constant. And this multiplies our charge that is stationary, but you needed to notice that it was incorrect. The units were incorrect, so you needed to divide by 1,000 to change it. So this is 0.0074 multiplying 10 times to the minus 3. Yeah, it allowed me to put it there. Great. All of these divided by our initial distance, but once again, you need to change centimeters into meters by divide by 100. So you can do it directly in the calculator if you want to. So this is what you're doing to change it into meters. Put everything in your calculator. Use your parentheses correctly. If you don't remember how to do that, you can do the top first and then find out what the bottom is second, and then divide one by the other to find the initial electrical potential. The value I got is 5.1 times 10 to the 5 volts. Okay, so we're not done. Now we need to find this final potential. So let me get another page right here. And our potential final, once again, is our constant. I'm going to just put it directly because it's the same formula, times 10 to the 9. Our charge has not changed. It's still 0.0074 multiplying times 10 to the minus 3 to make it into coulombs. Or you can divide it by 1,000 if you want to. Divide it by our final position. Our final position is 85 centimeters. So you need to make it into meters by dividing by 100. You can place it like this. Put it all in your calculator, and the value for your final electrical potential should give you a number like this, 7.8 times 10 to the 4 volts. Okay. Now, if you remember to calculate our difference, we need to do final minus initial, and you have everything. So place everything in your calculator. 7.8 times 10 to the 4 minus 5.1 times 10 to the 5. So what you need to do to find your difference of potential. When you do it in your calculator, let me put difference in potential. The value you should be getting is minus 4.3 times 10 to the 5 volts. This is the number you should be getting. Now, are we done? No, because that's not what they were asking for. They were asking for the change in potential energy. And this is the formula that allows you to calculate that. The charge that is movable times the change in electrical potential. We have everything. Just need to notice that the movable charge had incorrect units, so you needed to change that. And that is 0.0018 multiplying 10 to the minus 3 to change it into coulombs, multiplying this right here. Okay, I put it's multiplying. I'm gonna put it down here, but it's 4.3 times 10 to the 5 volts. And if you do it right in your calculator, you should be getting a potential energy of minus 9.8 times 10 to the 10 joules. And once again, I forgot to change it to yellow, but hey, this is new to me. But this is the answer that they were looking for. Hopefully this made sense to you. Remember that on Friday, if something didn't make sense to you, you can always ask questions, and I'll try to do my best to explain it to you online. Okay, now we need to do number 3. Extra practice number 3. Let me copy the answers. So remember that if your answer is correct, move on. Just continue with instruction. Let's see, the value I see here in my solutions manual says that you should be getting potential energy value of minus 4.5 times 10 to the minus 5, no, minus 5 joules. Okay, So if you got this value, you're done. Move on. Okay? But if you didn't, watch me solve the problem. Let me read this problem. It says, a 4.1 millicoulomb charge is moving towards a stationary charge that is negative 9.5 millicoulomb. What is the charge in potential energy experienced by this positive charge if it starts 1.8 meters away from the fixed charge and moves to only 0.52 meters away from the fixed charge? I like to draw things. I think drawing helps us visualize what's going on. So let me change my pen to white. And let's see if we can draw what's going on here. Okay, what they are giving me, what they're asking, and so on. Okay, this is my fixed charge. That is my movable charge. There are a certain distance. We're going to see what they say in the problem. The moving charge has a value of 4.1 millicoulombs. So everybody notice that this is incorrect. You need coulombs. So we're going to have to change the units by multiplying by 10 to the minus 3. The stationary charge, according to our problem, has a value of negative 9.5 millicoulombs. Okay. They're asking for the potential energy. So our question is going to be potential energy. We'll just change the potential energy. That's our question. Okay, great. And if you remember, that is going to be the value of this charge multiplying the change in electrical potential due to the fact that it's moving. So it's going to have different positions in different parts of the problem here. Okay, it starts 1.8 meters away. So our initial distance, the two of them are 1.8 meters away. And that's good. Meters are good. Great. What else? And moves to only 0.52 meters away from the fixed charge. So let's see. What is going on? Those two charges are attracted to one another. This is negative, this is positive. That means it's attracted to the negative charge. It will be moving. It will be moving this way. But read to see what it says. It says that it moves to only 0.52 meters away from the charge. So basically, they are giving us this distance right here. They already give us the distance, okay? We don't have to minus it from this one right here. We already know that our final, I'm going to put it here, our final is going to be at that 0.52 meters. I hope that makes sense to you. Okay, let's go for it. This is what we need to solve. Okay, this is the formula that allows us to solve the potential energy, but we're missing this. So let's solve for this. Next page. I don't need a highlighter, I need a pen. And you already know that the change in electric potential is potential final minus potential initial. Make that minus a tiny bit stronger. Okay, let's divide this and conquer. So let's start with the final this time. It doesn't matter which one you start with. So your final is going to be Q. All of them are the same constant for coulombs. The stationary charge divided by the distance that was final. Okay, so this is 9.0 times 10 to the 9. Always multiplying our stationary charge after you have changed it to coulombs, so negative 9.5 times 10 to the negative 3. Great. Divided by our final destination, 0.52 meters. It was already meters, so that was great. The value, if you put everything in your calculator, should give you a value of negative 1.6 times 10 to the 8 volts. Okay, so we have the first part of this equation solved. Next, we're now doing initial. So initial, once again, is K, Q, R. So there you go. This has not changed at all. I'm just putting it here because this is the same we did before. Our charge was negative 9.5. We need to multiply it by 10 to the minus 3 to make it into coulombs. And now we need to find our initial position. And if you remember from the problem, that initial position was 1.8 meters. Put all of these in your calculator, do the math, and you should be getting an initial electrical potential of minus 4.8 times 10 to the 7 volts. You have everything now. The change in potential is your final. And your final was, do I have it here? I think I already put it directly in the calculator. So let me erase these and show you what I did. I already calculated the change in potential energy by doing my Q, which was 4.1 millicoulombs. I needed to multiply that by 10 to the minus 3 to make it into coulombs. And then I put it directly here. I put my final minus 1.6 times 10 to the 8 minus, okay? I'm going to put it, I'm going to do it like this so you can see that this is what I'm doing. Minus 4.8 times 10 to the 7 volts. Okay, so these are all the numbers I need here. This was my little Q, the movable charge, and this is a difference in potential energy. Sometimes I don't like to do it separately, I just put it all in my calculator. So just remember that you're having minus, that turns into a positive. So if you did this, let me go back. Okay, I'm sorry about this. Let me plug in my computer. I didn't realize that it was not plugged in. Okay. I'll get better at this. So next page, your final potential energy is what I showed you before. The value is negative 4.5 times 10 to the 5 joules. Okay, 5 is a little bit weird. And you're done. So this is it for the examples for this section, for the extra practice problems. So let's go back to instruction. We just did this. Let me change my mouse so I can move. And here we go. More to know. Of course, there is more to know. Potential difference is how we rate batteries. So the potential energy, the difference in potential energy, your potential difference, is how we rate batteries. For example, a D-cell battery has a number of 1.5 volts battery. What does that mean? This means that the change in potential energy in that battery between the positive and negative end of the battery is 1.5 volts. If a charged particle moves from the negative side of the battery to the positive side, it will move through a potential difference of 1.5 volts. Notice that this is negative to the positive. You have a positive difference right here. But if a charged particle moves from the positive side of the battery to the negative side, it will move through a potential difference of negative 1.5 volts. Let's keep moving. If you want to learn more, this is not in your book, but you can read more about it. And this is the same thing we just talked about, but a different way of looking at it. I just added it in case you need more information or you like more information about batteries. It's up to you. Okay, here we go. Let's talk about the electron volt, EV, on page 463. Well, what is that? Well, the decrease in potential energy when an electron moves through a potential difference of exactly 1 volt. So these are your charges that are stationary. The potential energy created by this electrical field is 1 volt. Here you have your electron moving, okay, attracted to the positive charges. So the decrease in that potential energy, because it's moving, it becomes kinetic energy. That is the electron volt. The electron volt is an energy unit that is convenient to use when dealing with things on the atomic level, so very small, okay? You know that the charge for the electron is negative 1.6 times 10 to the minus 19 coulombs. We have used that before. The proton would have the same value, magnitude, but with a positive here, if you remember that. So if you calculate the potential energy that this electron creates, or has, okay, is the charge times the difference in potential, electrical potential here, and we said it was 1. So that value is 1 electron volt. 1 electron volt is negative 1.6 times 10 to the negative 19 joules. That's what an electron volt is. Okay, conservation of energy in an electric potential. Conservation of energy. You already know these, okay? You know that if potential energy disappears, in parentheses, it's because kinetic energy is increasing. Energy is not created or destroyed, it's just transformed. So if one seems to be decreasing, it's because the other one is increasing. We have done this before. The total amount of energy cannot change. So this is an equation we're going to be using next. The change in potential energy is because you have kinetic energy that is increasing. Or if there's a decrease in kinetic energy, it's because the potential energy is increasing, okay? They're opposite. What happens to one is the opposite of what happens to the other. Kinetic energy can be calculated using this equation right here. Kinetic energy is 1/2 the mass of our particle multiplying the velocity. This is not electrical potential, this is velocity of our particle squared. And we're still using the same equation we used before for potential energy. Is our charge that is movable times the change in electrical potential due to the fact that you're changing position within the electrical field. Okay, let's see how this works. Let's look at example 14.3. How does this work? It says a freely moving negative 15.1 millicoulomb charged particle, and they give us the mass in kilograms. This is nice. This is not so much. You're going to have to change it. Is placed 13 centimeters, wrong units, from fixed negative 2.0 coulombs. This is good. If the particle starts at rest, at what speed will it be moving when it is 95 centimeters, wrong units, away from the fixed charge? Okay. Let's see what we do here. Let me get my example so I have my numbers in front of me. Example number 3. So here we go. Let me go to my whiteboard right here so I can write something about this. We're doing another page. And this is example number 3, okay? That's what we're doing. 14, to be more specific. 14.3, so example 3. I like to draw things. It's up to you, okay? But I like to draw things. I know I have a stationary charge, I have a movable charge, and I'd like to know who is who. My freely moving, so that's my little q, is negative 15.1 millicoulombs. Okay. They give me the mass of this charge. The mass is 2.34 kilograms. Okay. My 4 here is a little bit weird. And it's placed 13 centimeters from a fixed charge. So my distance here initially, this initial distance, okay, is 13 centimeters. My fixed charge is negative 2.0 coulombs. Nice units right there. They're both negative, so I need to notice that they're both negative. That means that the movable charge is going to try to get away. If the particle starts at rest, so the particle starts at rest, velocity initial equals 0, okay? Starts at rest. at what speed will be moving when it is, so it keeps on moving that direction. My final distance is 95 centimeters. It got away up to 95 centimeters. I hope everybody understands that part. And now they want to know the velocity final here. What's the final velocity? Maybe I should put velocity. How are we going to... Not to be confused with electrical potential. This is velocity we're talking about. I'm going to put, question is velocity final. At this point, when it reaches this position right here. So now I have my problem all set for me. I understand what they're asking. I understand what they're giving me. I have noticed that my units are incorrect in some places. So I need to decide, where am I going to find this final velocity? Well, the only place, the only formula we know has a final velocity is our kinetic energy formula says that 1/2 the mass of my particle times the velocity final will give me that velocity. Does everybody agree with me? Everybody sees how this is done? Okay, I need to isolate this velocity right here. I need to modify this to have velocity. So my velocity, if you remember, anything multiplying goes on the other side. Dividing goes on the other side. Multiplying, anything multiplying goes on the other side. Dividing. So rearrange this and it will look like this. 2 times kinetic energy divided by my mass. Remember that the root here comes from the fact that I need to get rid of this square. So this is the formula that's going to allow me to calculate my velocity. What do I have? What do I need? Well, I do have, the number 2 doesn't change. I do have the mass for my particle, but I'm missing this. I'm missing my kinetic energy. I don't know what my kinetic energy is. I need to find that. Okay, well, let's go back to a new page here. Go back to a pen. Where do I find how much kinetic energy I have? Well, I know that the changes in my potential energy translate into my changes in kinetic energy. Okay, so if I can calculate my potential energy, I will know what my kinetic energy is, correct? So far, so good. So do we know what our potential energy is? So this is one formula that we need to use. I don't know what my potential energy is yet. I need to find this. But I know how to find this. We have been using the formula that allows us to do that. The change in my potential energy equals my movable charge times the change in electrical potential. Well, this is also missing. Okay, we do have the charge that is movable, the value for that little q we have, but we don't have these. So this is a problem that keeps on going. We need to find this change in electrical potential. And if you remember how to do that, I think I'm on this already. This is going to be our final minus our initial. And don't confuse velocity with electrical potential. We're talking about electrical potential here, okay? I'm going to put it directly in here, both of them, just because I like to do it this way to save time. So remember that this is 9 point, each one of them, to calculate this, you need this formula. V equals K, Q, stationary charge, and distance, okay? Initial for the initial and final for the final. So this is what you're trying to do for each one of them. So I'm doing first the final. That means I'm gonna need to use a final distance. But K is the same for everybody. 9.0 times 10 to the 9. I'm not putting units because it takes too much space. multiplying my Q. My Q is my stationary charge, and my stationary charge is minus 2.0 coulombs. It's already in the right units. My final destination is 0.95 meters, okay? So this right here is my final, okay? My final electrical potential. Now I need to minus my initial electrical potential. The top has not changed. 9.0 times 10 to the 9, multiplying, minus 2.0. And now I need to divide these by my initial position, and that was 0.13 meters, okay? I need to have meters. You can solve these one step at a time, or if you know how to use your parentheses really well in your calculator, you can put everything in your calculator. And the value here for this change in electrical potential is, let me find it, 1.2 times 10 to the 11 volts. Okay, so we have this solved right here. This was just, let me go to the previous. This is just this part right here. Okay, this is all we have solved, is this part right here. So let's go to the next one. Do I have enough room? Yeah, I do have enough room. So now I need to go ahead and find that potential energy. The potential energy is my movable charge in coulombs, so minus 0.0151 in coulombs, multiplying the value of my electrical potential difference that I just found, 1.2 times 10 to the 11. Put everything in your calculator and you should be getting a value of negative 1.8 times 10 to the 9 joules. Now, remember, we just solved for the potential energy, but that's not what we needed. We needed the potential energy so we could find the kinetic energy, and they are inversely related. If this goes up, this one goes down. If this one goes up, this one goes down, and so on. So change of signs is what we need to do next. Let me go to this. So my change in potential energy is the opposite of what happens to my kinetic energy. So my kinetic energy, my change in kinetic energy equals 1.8 times 10 to the 9 joules. I hope everybody agrees with me. Are we done? Now remember that a change in kinetic energy just means kinetic energy final minus kinetic energy initial. But in the kinetic energy initial, it was a rest. That means that our velocity initial was 0. That means that this can be disregarded. Okay? Our kinetic energy final will give us the velocity. And we just have to equate to this value right here. So let's go to a new page right here. No, that's not it. Create a new page. Okay, here we go. Let's see. Where am I? Yeah. Kinetic energy, change in kinetic energy is equal to our kinetic energy final, because remember the initial disappeared because the initial velocity was 0. And remember this has a formula of 1/2 the mass of our charge multiplying the velocity square. And that's where we found the velocity square. Velocity equals 2 times the kinetic energy we just found divided by the mass. We have everything we need. We just need to put it in our calculator. 2 times our kinetic energy was 1.8 times 10 to the 9 joules divided by the mass of our particle in kilograms, which they gave us in kilograms already. Put everything in your calculator and your velocity final should give you a value of 3.9 times 10 to the 4 meters per second. Remember that you need to put units in your values. And I'm going to put it a square around in yellow. Okay, so this completes example number 3. Let's go back to instruction. Notice that you need to do extra practice problems 4 and 5. So once again, I'm going to put the value for the final answer. If you got it right, move on. And if not, watch to see how it's done. Okay, go back to my whiteboard here if I can. Okay. Another page. Okay. So let's see. I'm trying to find the answers here. For number 4, where are you? Okay. So number 4, your velocity should be 1.3 times 10 to the 3 meters per second. If you got this, move on. If you didn't, watch to see how this was solved. And let me get my notes because I have not memorized the numbers. I don't have all those numbers memorized. Let's read the problem first. Always read the problem, try to figure out what they're saying to you, what they're giving you, and so on. It says, a negative 33.3 millicoulomb charged particle with a mass of 550 grams is placed 2.4 meters from a stationary negative 9.8 millicoulomb charge. If the particle starts at rest, how fast will it be moving after it has traveled 1.5 meters? Now remember, I like to draw what they're saying to me. I think it makes it very clear what they're giving me, what they're asking. So I always start by drawing my stationary and my movable charge, and then putting the information underneath that they're giving me. It says that the movable charge has a value, let's see, where is it? 33, minus 33. 0.3 millicoulombs. Okay, that's a pretty big charge. Wrong unit, we're going to have to change it into coulombs. It gives us the mass. The mass for this is in grams. That's a big no-no too. 550 grams. We're going to have to change that into kilograms. And its place initially, so our initial distance right here is 2.4 meters, and the units are correct here, so we don't have to worry about these. The stationary charge is negative 9.8 millicoulombs, wrong units as well. Both of them are negative, so they don't like each other. This is going to try to move away. Everybody sees that. It says if the start particle starts at rest, so our velocity initial equals 0, that's going to make our kinetic energy initial 0 too, okay? This means kinetic energy initial is going to be 0, okay? What else? Starts at rest, how fast will it be moving after it has traveled? So it is traveling an additional 1.5 meters. Everybody, please notice that our final position is the addition of 2.4 plus whatever else it has traveled. So our final position is 2.4 plus that 1.5 that it travels to move away. So our final position is actually 3.9 meters. That was tricky. They were trying to trick you, okay? Once again, the question is, how fast will this particle travel? So they're asking for the final velocity, okay? Final velocity. Velocity final is our question. Okay, move on. Where do we find velocity final? Okay, the change of kinetic energy, remember, is kinetic energy final minus kinetic energy initial. But this has become 0 because the velocity was 0 initially. So our final velocity will give us our final kinetic energy will give us the final velocity. And kinetic energy, if you remember the formula, looks like it's 1/2 the mass of our particle that moves times the velocity square. And we already learned that velocity is the square root of 2 times our kinetic energy divided by our mass. So this is the formula that will give us the final velocity. But we are missing this. Okay. Remember that this comes from this other formula. Change in potential energy will give us our change in kinetic energy. So this formula allows us to find this kinetic energy that we are missing. But once again, we're missing something. We don't have these. So where do we find these? Our change in potential energy equals our charge times our change in electrical field. Oh, goodness, we are missing this. We don't have this. And if you remember how to find this, the change in electrical field equals the electrical field final minus the initial. So this is all everything that we need to do step by step. We cannot do anything until we find our electrical field. Once we have that, we can put it in this formula to find the potential energy. Once we have potential energy, we find kinetic energy, and then we can place it in here to find the final velocity. Okay, so let's go and find our all the different potential energy, electrical potentials. Mouthful here, I'm getting tired of saying it, but here we go. I think for this one, I broke it into the different parts. So I'm going to start finding my final. So I didn't put it all in one equation just because I like to do it different ways so people can see it different ways. But remember that this is just our constant for Coulomb, the charge that is stationary, the value for that, divided by the distance that was final. So what is that? 9.0 times 10 to the 9, multiplying our charge. And if you remember, that was in the incorrect unit, so you need to multiply by 10 to the minus 3 to make it into coulombs, divided by that final distance that we found, 3.9 meters. Do the math, and you should find a value for the final electrical field of minus 2.3 times 10 to the 7 volts. Okay, now we need to find our initial electrical field. Sorry, electrical potential. Electrical potential. Our initial electrical potential. Same, 9.0 times 10 to the 9. Multiplying still our charge that is non-movable. 9.8 times 10 to the minus 3 in coulombs. But now divided by our initial position. And if you remember, that position was 2.4 meters. Do the math, put it in your calculator, and the value you should be getting for this one is minus 3.7 times 10 to the 7 volts. Now you need to do the difference between final and initial. You need to do that. But I'm not going to do it now. I'm just going to do it directly into my formula for potential energy. I'm showing you that you can do it just directly. Remember what this was. This was our movable charge, which is minus 33.3 multiplying 10 to the minus 3 because we needed to change that into coulombs. And now you can put directly the minus in here. I'm going to put a bracket because I have several negatives. 2.3 times 10 to the 7. Should I put okay. Minus 3.7 times 10 to the 7. And close your bracket. I can put everything in my calculator. You can also just do these separately if you want to. So that's my final electrical potential minus my initial potential. Okay, that's what it is. And I find that my potential energy, my difference in potential energy, equals minus 4.7 times 10 to the 5 joules. Okay. So if you remember, let's see if I have it here. No, that's not it. Maybe I just have to go to, go down. I lost it. Previous. Here. If you remember, my kinetic energy now is just going to be the same as my potential energy, but with a sign change. Okay, so I'm gonna do another page here. So I'm gonna say that my potential energy equals my kinetic energy with inverse signs. And I just found this. I just found my potential energy. So my kinetic energy, my change in kinetic energy equals positive 4.7 times 10 to the 5 joules. Okay. Now I can put this in my velocity equation. 2 times my kinetic energy, 4.7 times 10 to the 5. I'm not going to put units right this minute because it takes too much space and takes time. But you need to notice that my mass was incorrect. They give me 550 grams, okay? So divide this by 1,000 to find your kilograms. And then you'll be getting that 1.3 times 10 to the 3 meters per second. And that was your answer to this problem. This was your answer, okay? So this is done. I hope it made sense. If not, ask me questions on Friday. Okay, another page. Now we're going to do number 5. Number 5. The answer for number 5, let me get my solutions manual here, so I just copy the answer, is 7.9, what a weird 9, times 10 to the 5, oh my goodness, meters per second. Okay, that's the velocity you should have found for the particle. If you didn't, watch the video to see how I solved this or how it's solved. Okay, here we go. Change of color. Let's read the problem first and see what is what. 5 reads like this. A 5.6 Coulomb charged particle with a mass of 2 kilograms is placed 42 centimeters from a stationary negative 3.7 Coulomb charge. If the particle starts at rest, how fast will it be moving after it has traveled 24 centimeters? Okay, everybody, I like to draw. I think it makes sense. My stationary, my moving particle. Okay, that Q turned out a tiny bit weird. I'm going to try again. Erase that Q. Go back to the pen. Okay, so here we go. And I'll make a distance because I know that information is going to be given to me, so I already start with that. So let's say the 5.6 charged particle is the one that's moving. So I'm going to put this value here, 5.6 coulombs. We're not going to have to do anything about that. And they give us the mass to be 2 kilograms, 2.0 kilograms, significant figures. And it's placed initially, so we have our initial distance here between the two of them to be 42 centimeters. That's a big no. We're going to need to change it into meters later by dividing by 1,000. The stationary charge, on the other hand, is negative 3.7 coulombs. The particle starts at rest, so our velocity initial equals 0, making our kinetic energy initial 0. Okay, if it's not moving, it doesn't have kinetic energy. That makes sense? How fast will it be moving after it has traveled 24 centimeters? Negative, positive, they are attracted to one another. This is moving this way. It's moving this way 24 centimeters. What does it mean? Is that the final position for this particle? No, the final position is going to be here. Okay, this is how much it has traveled out of those 42. So my final position is going to be my 42 minus the 24 that it traveled. And that is going to be, okay, I'm sorry, being stubborn, 18 point, both of them need zeros, so 18.0 centimeters. Okay, this is my final position. Now I have everything I need, and I notice the units that need to be changed. So next page, let's see how we solve this. It's exactly like the one before. It just, the final destination was a tricky part, but our velocity, if you remember from the videos before, equals the square root of 2 times the kinetic energy divided by the mass. Okay, that comes from our kinetic energy formula. And I'm not going to put it here because we have been seeing this formula over and over and over. I need kinetic energy again. I need that kinetic energy. Well, how do I find that? I find that by using this formula. I know that the change in potential energy is the opposite of my change in kinetic energy. So if I can find my potential energy, I'll know my kinetic energy. Remember, this kinetic energy now has become our final kinetic energy with a final velocity because the initial was gone. Okay. Now, how do we find that potential energy? Well, we know it's the movable particles charge times the change in electrical field. So we're moving along. We still have to find this. We know that our electrical field, the changes in it, has to do with the position of the particles. So final versus initial is how we find that change in the electrical field. So let's move on, new page, and velocity final. Remember that all velocity, electrical field, I'm getting tired here, equals our constant times the charge that is not movable, our stationary charge, divided by the distance. So I'm going to put it directly here so I don't have to write it over and over and over, but it's 9.0 times 10 to the 9, multiplying our charge that is not movable, so minus 3.7 coulombs, divided by our distance that was final. We found that to be 18 centimeters, but remember that we don't need centimeters, we need meters. Please divide that number by 100 to have your meters. And the value here is minus 1.9 times 10 to the 11 volts. We do the same thing for our initial electrical field. 9.0 times 10 to the 9, multiplying our charge at stationary. But now we divide this by our initial position, which was 42.0 centimeters. So no, divide by 100 to make it into meters. Put everything in your calculator, and if you do it right, try until you get it right, you need to find a number like this, minus 7.9 times 10 to the 10 volts. Now remember that to find your change in electrical potential, you need to do final minus initial. So take this number and minus this number. This number minus this number is going to be minus, and then negative is a positive, so you're going to be adding them. So what do you get? What do you get? Let's do another page, and you should find, actually I didn't do it separately. Yeah, I did separately here. I have another value here. So this number is negative 1.1 times 10 to the 11 volts. Did both separately and together. Okay, so that's your change in electrical field. Potential. Now we can calculate that potential energy. Movable charge, what was that? 5.6 coulombs. Multiplying what we just found, negative 1.1 times 10 to the 11. If you do this correctly, your potential energy has a value of negative 6.2 times 10 to the 11 joules. Now remember what we said. The kinetic energy is the opposite of the potential energy. So my kinetic energy is going to be the same magnitude but opposite sign. 6.2 times 10 to the 11 joules. So if this one disappears, this one is increasing. So now I have everything I need to calculate my final velocity. Velocity equals the square root of 2 times the kinetic energy value I just found. Extend this. Divided by the mass, and that was given to us. It was 2 kilograms. So do the math, and your value right here is the 7.9 times 10 to the 5 meters per second that I mentioned at the beginning of the video. Let me get yellow so I can square this. That was the value that you needed to find. Okay, number 6. Number 6 is a tiny bit different. I mean, it's the same formulas, but a tiny bit different. So let's see. Let me get yellow. I think I have yellow, but I'm not sure. Yeah, number 6. Number 6